This chapter we get to talk about square roots and Pythagorean theorem. So the square root of a number is one of two equal factors. If you divide a number by its square root, you get its square root. The square root multiplied by itself gives the number. The radical sign, which looks like this if you don't put the line over the actual number, is used to indicate a square root. In North American conventions, the square root is positive unless you specify that it's plus minus. However, in some other places, such as Asia, the square root is by default both positive and negative. For example, find each of these square roots. Well, 1 is equal to... 1 is equal to 1 times 1, right? Therefore, the square root of 1 is equal to 1. You can always also say that this is the square root of 1 squared. Wait a second. What about negative 1 times negative 1? Well, that also equals 1. That's why in many places the convention is that the square root is plus minus by default. But hey, if it's specifically marked, like this negative square root 16 here, well, for North America, that would mean it's negative square root of 4 squared. Because 16 is equal to 4 squared. It's also equal to negative 4 squared, but for North American purposes, no, we're not bothering with that. So in North America, the square root is for the positive square root. And because positive 4 times positive 4 equals 16, the square root of 16 is equal to 4. And since there was a negative symbol in front, well, it's going to be negative 4. The square root of 0.25 is the square root of 0.5 squared. So you get 0.5. Now for the square root of 25 over 36, well, 25 is 5 times 5. 5 squared over 6 squared. Or you could put 5 over 6 in brackets squared. If you square root a fraction, you are square rooting both the top and the bottom. You're square rooting the whole thing. So you end up with 5 over 6. You could also write the root of 5 over 6 squared. Yeah. And then that equals 5 over 6. Example 5. Solve a squared equals 4 over 9. Well, if a squared is 4 over 9, then a is equal to the square root of 4 over 9. Well, okay, if we want to show more explicitly that we're doing the same thing to both sides, it looks like this. The square root of a squared, so a, is equal to the square root of 4 over 9. And we know that that's going to be 2 over 3 squared for 4 over 9. And we square root this thing, and we just get 2 over 3. Okay, find each of these square roots. The square root of 4, well, 2 times 2 equals 4. 2 squared equals 4. The square root of 4 is therefore equal to 2. The square root of negative 49, well, the thing is, you can factor this. Like, it's possible to factor out in square roots. You'd get square root of negative 1 multiplied by square root of 49. Because the square root of a is equal to a to the 1/2 power. because the square root squared is equal to the original value. Therefore, the square root of AB is equal to AB to the 1/2 power, which is equal to A to the 1/2 power times B to the 1/2 power. So, therefore, square root of AB is equal to square root of A times square root of B. So, the square root of 49, we know that 7 times 7 is 49. 7 squared is 49. Therefore, the square root of 49 is 7. So 7 times square root of -1. If you try to put in a negative value and then square root it on your calculator, it will tell you error, unless your calculator is a pretty sophisticated one that allows the use of imaginary numbers. So this, we say that it doesn't exist. But later on, when we get to imaginary numbers instead of just real numbers, well, we would be able to work with this. Does not exist. Well, I mean, it's not real. Real. This is imaginary numbers. Okay? So the square root of 0.01 would be, now we know that we can't square root negative numbers, but what if we have decimals, like values less than 1? Well, what is 0.1 times 0.1? I mean, it's equal to 0.1 squared is 0.01. So the square root of that is equal to 0.1. Negative square root 0.64 is equal to negative square root 0.8 squared. So that's negative 0.8. Square root of 9 over 49, that's equal to square root of 3 over 7 squared, which is, of course, going to leave us with 3 over 7. And then negative 1 over root of 1 over 25, that's going to be negative square root of 1 over 5 squared. And so when we open the square root, the square inside also gets canceled out. Because what this is doing is saying 1 over 5 squared to the 1/2 power. And we know that when you open up a series of exponents, when you simplify them, these multiply together. And what is 2 times 1/2? It's 1. So, negative 1 over 5, because there's a negative symbol here. Otherwise, it would just be 1 over 5 under North American convention. Now let's solve these equations. X squared is equal to 121, which means square root of x squared is equal to square root of 121, which is, we know that 121 is equal to 11 squared. Common squares are pretty common to remember up until about 15 or so usually. So square root of x squared is just going to be x, and square root of 11 squared is just going to be 11. If this was Bayesian convention, we would go plus minus 11. A squared is equal to 3600, while square root of a squared is equal to square root of 3600. 60 times 60 is equal to 3600. 60 squared. So a is equal to 60. P squared is equal to 49 over 100. So P is equal to the square root of 7 over 10 squared. So it's just equal to 7 over 10. Actually, since we went with that format anyway, over here we might as well write this down to show the symmetry of steps. Okay, what happens if we don't go square root of t squared? Well, yeah, you could just put t. But then, I've been showing what exactly is being squared under the radical just for y'all's convenience. But really, you can go square root of 121 over 225 for denominator and numerator can be done separately. So you'd get square root of 121, which is 11. Well, okay, yeah, we might as well write this down. So 11 over square root of 225 is 15. Yeah, so this is the sort of thing that's happening, but eventually you just omit this middle step altogether. Or it's going to be t equals square root of 121 over 225, and then just straight to this. The estimation of square roots. Most numbers are not perfect squares. You can estimate square roots for these numbers. For example, the square root of 200 to the nearest whole number. Well, we know that 14 squared is equal to, even if we didn't remember this, we can find this. It's 196. And 15 squared is equal to 225. So square root of 200 is close enough to the square root of 196. Therefore, it's approximately 14. Now, estimate the square root of 76.2 to the nearest whole number. Well, 8 squared is equal to 64. 8 times 8 is 64. 9 times 9 is 81. And 76.2 is much closer to 81. It says to the nearest whole number. That's why we're just going to do this and genuinely estimate instead of, well, brute force method. This is approximately the square root of 81. So that's approximately 9. Okay, exercises. Estimate to the nearest whole number. The square root of 10. Well, it's approximately the square root of 9. And we know that 9 is 3 times 3, so 3. The square root of 14. Well, that's close enough to the square root of 16. So it's going to be approximately 4 to the nearest whole number, that is. It's much closer to 16 than to 9, that's for sure. And 26. It's approximately the square root of 25. So that's approximately 5. The square root of 47, oh, that's closer to 49 than to like 36, right? So, square root of 49, we know that 49 is 7 times 7. Therefore, square root of 49 is going to be 7. Square root of 103, oh, that's pretty close to the square root of 100. And we know that 10 times 10 is 100, therefore square root of 100 is 10. Square root of 17.3, well, that's close to the square root of 16, because it's way closer to 16 than to 25. So it's going to be approximately 4, because 4 times 4 is 16. Therefore, the square root of 16 is 4. Square root of 50.5, oh, 50.5 is pretty close to 49. And we know 49 is 7 times 7. Therefore, the square root of 49 is 7. The square root of 175.2, Well, 13 squared is 169. 14 squared is 196. 175.2 is much closer to 169. Root 175.2 is approximately root of 169. Compared to 196, that is. So, this is approximately 13. Oh look, it's the obligatory problem-solving section. This time we're supposed to use a Venn diagram to use some problems. What do Venn diagrams do? Well, Venn diagrams represent how your groups can overlap. Like say you have 25 skiers. That means the whole rectangle is total equals 25. Okay, and 13 signed up for the downhill race. Let's say this is D. And 8 signed up for the ski jump contest. So this is J. Okay? So, 6 skiers signed up for both. How many skiers did not sign up for either contest? So we know that both D and J, there were 6 people who decided to do both. 13 total signed up for the downhill race. So in total, D has 13 people. Now there are 6 who also choose J, so there are 7 who didn't choose J. There were 8 who signed up for the ski jump contest. 6 of them also signed up for downhill racing. So there must be 2 who didn't sign up for downhill racing. How many skiers did not sign up for either contest? Well then, you have 7, 6, and 2. So that's a total of 15 people who signed up in one or both contests. Therefore, there must be 10 people outside who signed up for neither contest. By diagram, 10 signed up for neither. If you have 3 different groups, you just add another circle to your Venn diagram. However, when you get to 4 or more groups, Venn diagrams start getting really complicated to draw. So for now, we stick with 2 or 3 groups. Now let's do an exercise. Let's figure out the number of people who didn't want to play either football, i.e. American football, or soccer, which is known as football to most of the world. Because American football is like hand lozenge or something, if you want to name it more appropriate to what you actually do in it. So, of the 90 students surveyed, total equals 90. For this whole sample space, the whole box, 27 wanted to play football, 67 wanted to play soccer, and 15 wanted to play both. Okay, so football, American football specifically, and soccer, 15 wanted to play both. Okay then, besides these 15, how many people wanted to play football? Well, 27 in total minus 15 gives us 12 people who wanted to play football. And 67 people wanted to play soccer minus 15 would give us 52 people who wanted to play soccer. How many people did not want to play either sport in the fall? Well, 90 minus all these people. So how many are there? 2 plus 5 plus 2 gives us 9. 1 plus 1 plus 5 gives us 7. So 79. Okay, so 90 in total minus 79 leaves us 11 who chose neither. Now, depending on convention, you may want to write this number that's outside both bubbles in like the corner somewhere or something, just to show that, no, I'm not trying to label anything, and specifically in one of the lower corners. But conventions vary, so it's not that big of a deal. So our answer would be 11 did not want to play either sport in the fall. So this is how we use a Venn diagram to do our problems. We consider the people who chose multiple choices first, as many categories of them as exist, such as if you have 3 different circles. And then you consider how many people are left for, say, instead of chose all 3, there's chose every pair of 2. And then you choose the people who chose one thing only, and then you find the people who were excluded. That is generally how Venn diagram problems work. Of course, you may be finding different things depending on the problem. Now, the real number system, what we call natural numbers, can refer to whole numbers from 0 on up, but in some conventions, natural numbers do not include 0, which is really weird considering I naturally see 0 T-90 MS main battle tanks in this room right now. I wonder where they all went. So, some places have natural numbers including 0, and others don't. Just be kind of careful on which convention you're dealing with. And also, some places, for some reason, refer to 0 and positive integers as whole numbers for some reason. And given we have this term, positive integers, i.e. whole numbers that are bigger than 0, you'd think you don't need natural numbers to refer to positive integers only, right? But no, mathematicians, even though math is a very logical thing, it's done by people, which means sometimes it's, yeah, you get the idea. Conventions can get pretty funny. And integers include both positive and negative whole numbers and 0. Apparently in some places in the US, whole numbers just means natural numbers, so just be aware that sometimes you might be asked something like that. Okay, rational numbers can be expressed as fractions with integer numerators and denominators. So they can be expressed as some integer over some other integer. Irrational numbers cannot. Rational numbers, if you express them as decimals, will always repeat themselves or be finite in length. Irrational numbers are infinite decimal places and non-repeating. Square roots, in fact, radicals in general, if they are not whole numbers or finite decimals, such as, well, if you take the square root of 0.01, you'll get 0.1, which is a finite decimal, and therefore it's rational. Radicals that don't give you a neat answer like that, they give you irrational numbers. Name all sets of numbers to which each of these real numbers belongs. So, 7. Well, it's a natural number. Natural number. which, by the way, also means it has to be an integer. You can also say that it's a positive integer if you use that separately from natural numbers. And it's rational because it's a finite decimal. And it can be represented as a ratio of 7 over 1 or 14 over 2 or so on. 0.555 repeating? Oh, hey, it's a repeating decimal. It's a rational number. Now, if we consider the square root of 12, if you try that on your calculator, you'll find that it is not a repeating decimal. And that makes it irrational. Irrational. Okay. To compare each real number, you can write them as decimals and then compare the decimal values or approximate decimal values because root 5 is irrational, it's infinitely long, and it's non-repeating. So, root 5 is approximately 2.236. Well, here's the approximate decimal representation, and, well, exact for this one. So we can see that 2.25 is bigger than 2.236, and so on. So we mark this. Now let's name all the sets of numbers to which each of these real numbers belongs. Negative 11 is an integer. What else is it? Oh, it's also rational because you can show it as negative 11 divided by 1. You can also specify that it's a negative integer, but that's not too relevant for us. 5 and 4 over 7. Well, we know it's rational because you can represent it as a fraction. But it's not a whole number. It's not an integer. 0 is an integer. And it's a natural number. This is debatable though. And it's rational because any non-zero number as a denominator and 0 as a numerator will give you 0. 0 divided by 0, though, will give you indeterminate. And, well, what about negative square root of 99? Well, if you try to enter this into your calculator, you would find that it is an infinitely long, non-repeating decimal. We also know that square root of 99 is equal to square root of 9 times square root of 11. So negative 3 root 11. Negative square root of 99 we know is irrational because root 11 is irrational. And multiplying by negative 3 doesn't fix its irrationality. So let's replace each bracket with greater than, less than, or equal to make true sentences. I thought sentences had to have like subject, object, and like at least some vague semblance of grammar, other than one-word statements like yes. But hey, this is talking about mathematical sentences, not language arts. So 2.6 and root 7. Oh, what's root 7? Oh, it's approximately 2.646. Oh, it's going to be greater than 2.6 then. Okay. Root of 11. Approximately 3.3, which is less than 3.5. 4 and 1 over 5. Root of 18 is approximately 4.24, which is greater than 4.2. 3.7 versus root 14. Well, that's going to be approximately 3.74, which is greater than 3.7. Well, 3.7 is less than root 14, more like. The Pythagorean theorem describes the relationship between the legs and hypotenuse of any right triangle. The square of the length of the legs added together, those two squares, will equal the square of the hypotenuse. We give this as a squared plus b squared equals c squared, with a and b being the legs and c being the hypotenuse. The hypotenuse is the longest side of a right angle triangle. It's opposite the right angle. If you know two sides of a right triangle, you can find the third side, presuming that you know which one is the hypotenuse, i.e. one of the sides you have, or the side you're trying to find. The hypotenuse is 30 meters long. Okay, we're supposed to label and find the missing measure for each of these right triangles. So that's why the diagram is left blank for us. Okay, then, let's do some labeling. Hypotenuse 30 meters. Okay. One of the legs is 18 meters long. And round to the nearest tenth if necessary. Well, a squared plus b squared equals c squared, or c equals square root of a squared plus b squared if you prefer. So, 18 squared, this is b, like just unknown, plus b squared is equal to 30 squared. B squared is equal to 900 minus 18 squared is 324. So, b squared is 576. So, b is square root of 576. 576 square rooted, oh, it's 24. b equals 24. And the units are meters. And you may want to label this on your diagram as well. Now let's say the legs are 5 centimeters and 12 centimeters long. Be advised, guys, do not assume that a diagram is to scale unless it's specifically labeled as being to scale. So, a squared plus b squared equals c squared. 5 squared plus 12 squared equals c squared. That means c squared is equal to 25 plus 144. So 169 is equal to c squared. C is equal to square root of 169. This step here could be omitted if you so wished. And later on probably will be omitted. So C is equal to 13, and the units are centimeters. So 13 centimeters. Okay, let's do some exercises. Write an equation you could use to find the length of the missing side of each right triangle. Then find the missing length. Round to the nearest tenth if necessary. The legs are 5 meters and 8 meters. So, each right triangle, so yeah, right angle, 5 meters and 8 meters, a squared plus b squared equals c squared. C squared is equal to 5 squared plus 8 squared. So 25 plus 64. That leaves us with 89. C squared equals 89. C is equal to root of 89. So if we try that, round to the nearest tenth. Okay, C is approximately 9.4. And this is meters. 8 meters. C is approximately 9.4 meters. Let's say the hypotenuse is 25 and one of the legs is 7. Well, then what do we do? Well, 25 and one of the legs is 7. So we're looking for B. A squared plus B squared equals C squared. Which leaves us, it's best, instead of writing separate equations for A, B, and C, to just start with this base Pythagorean theorem equation and manipulate as necessary. 7 squared plus B squared is equal to 25 squared. So B squared is equal to 625 minus 49. So B squared is 576. B is equal to square root of 576. And that's equal to 24. What are the units? Oh, hey, there's no units here. That means we just put B equals 24. And haha, we have found the third side. So what if we know that A equals 6 kilometers, B equals 12 kilometers? Well, the convention is that C is a hypotenuse. Therefore, A squared plus B squared equals C squared. 6 squared plus 12 squared equals C squared. C squared is equal to 36 plus 144. So 36 plus 144 is going to leave us with 180. And therefore C is equal to root of 180, or approximately 180 square rooted 13.4, and the units are kilometers. Okay, A equals 10 meters, C equals 25 meters. Well, same old formula. It's much easier than trying to remember a bunch of separate formulas, which can just convert between each other really easily. So we're looking at 10 squared plus B squared equals 25 squared. B squared is equal to 625 minus 100. So B is equal to root of 525. Because I judge this subtraction sufficiently simple that you can just go straight to this step instead of spending a step simplifying to make sure everybody can keep track. Root of 525 will leave you with, oh, it's approximately 22.9. And the units are meters. Okay, then what if you got B and C but no A? Well, you still use the same old formula and manipulate as necessary. C squared plus 14 squared equals 21 squared. So 441 minus 196 equals A squared. So 21 squared minus 14 squared is 245. So A is equal to root of 245, which is approximately 15.7. And this is in feet for the units. Well, that's what rounding to the nearest tenth gets you. Even though it's like 15.65247584 and so on, this is an irrational number, just like basically every radical that doesn't end real quick. Using the Pythagorean theorem. We can use the Pythagorean theorem to solve problems. Whoa! You don't say! Really? I wonder why people invented the Pythagorean theorem, besides for solving problems. Like, amazing. No, okay, that is kind of stating the obvious, but let's say we have a ice hockey rink. Let's say it's 200 feet long and 85 feet wide. In actuality, professional ice hockey rinks, if I recall correctly, are not this rectangular. Like the walls are a bit more curved around the corners. What is the length of the diagonal of the rink? So in other words, from one corner to an opposite corner, 200 feet and 85 feet. So the length of the diagonal, let's say it's d, okay? D squared is equal to 85 squared plus 200 squared. So we're looking at 85 squared, 7225 plus 40000. So this is going to end up with d squared equals 47,225 square feet. But that means d is equal to square root of 47,225. So square rooted, it's approximately 200. Should we round? Because telling somebody that the length of your hockey rink's diagonal is the square root of 47,225 is not very useful to them. But if you tell them, oh, it's like 217.3 feet, yeah, it's a bit less useless. So, the question didn't say to round, so we'll keep both of these here. And if we had to put a statement, we would put the length of the diagonal is the exact value, root 47,225, or approximately 217.3 feet. Okay. Here it says, write an equation that can be used to answer the question, then solve. Round to the nearest tenth if necessary. Oh, okay. That means we have instructions to round if we need. What is the length of the diagonal of a square 100 meters long on a side? Well then, d squared is equal to 100 squared plus 100 squared. So that's 10,000 plus 10,000. So 20,000. Now d is equal to the square root of 20,000. Also known as 100 times square root 2, because it's equal to square root 2 times square root of 10,000. 100 square root 2. Eventually you'll be able to omit this step and go straight from square root of 20,000 to this. So 100 times square root 2 will leave you with approximately 141.4, because it's to the nearest tenth if necessary, and the units are meters. Okay. Number 2, how long is a kite string to a kite that's 25 meters above the ground and 20 meters away along the ground? 25 meters and 20 meters. And the string is S in this case. We assume that the kite string is straight, as this question kind of implies very strongly. So, S squared is equal to 20 squared plus 25 squared, which gives us 400 plus 625 equals 1025. S is equal to square root of 1025. I mean, sure, you can factor out a root 25, i.e. a 5, out of this thing, but there's really no particularly need. It's not like it leads to anything particularly common as one of the numbers under the radical. So square rooted, we get approximately 32.0 meters. It's like 32.015621119 and so on. That's as many as my calculator shows, but it said to the nearest tenth. So we will go to the nearest tenth. So how high is a ramp of 15 meters slant length that wait a second. It's 14 meters along the ground. Well, this is a very much not to scale diagram. 15 meters slant length, that means the slope itself is 15 meters long, and this is the height. So, 15 squared is equal to 14 squared plus height squared. Therefore, height squared is equal to 15 squared, which is 225, minus 14 squared, which is 196. So we're dealing with 29. And that means height is equal to square root of 29, which is approximately 29 square root, 5.385 and so on. So 5.4. And the units are in meters. So yeah, we should relabel that. Height. If you have a Cartesian grid, also known as a coordinate plane, you can find the distance between 2 points using Pythagorean theorem because the axes are at right angles to each other. Therefore, the difference along one axis and the difference along the other axis, these are the legs of a right triangle. Let's find the distance between points 1, -3 and 5, 4. 1, -3 and 5, 4. Okay, so horizontally, that's a distance of 4. And vertically, that's a distance of 7. So the overall distance between these points, distance is equal to square root of distance in the x-axis. You can use x2 minus x1 squared plus y2 minus y1 squared. So that would be 5 minus 1 squared plus 4 minus -3 squared. So you're dealing with 4 squared plus 4 plus 3, so 7 squared. Which means root of 16 plus 49. So that is root of 65. That is the exact value for the distance between 0.1, -3, and 5, 4. So that is the distance in exact value. If you had to round, then you would put it into your calculator and give an approximation. For exercises, let's find the distance between each pair of points whose coordinates are given. Round to the nearest tenth if necessary. Well, the distance is the square root of difference in x squared plus difference in y squared. Which means the square root of difference in x is -5 minus 1 squared. Difference in y, -8 minus 1 squared. Okay, so that's going to be -6 squared plus -9 squared. So that's the root of 36 plus 81. So root of 117. The root of 117 is approximately 10.8 for the nearest tenth. Okay, what about -2, -4, and 2, 3? Well, -2, -4, and 2, 3, we have the same old formula. x2 minus x1 squared plus y2 minus y1 squared. So that's root of x2 is 2 minus -2 squared plus 3 minus -4 squared. So 2 plus 2 is 4, 4 squared, plus 3 plus 4 is 7, 7 squared. So that's root of 16 plus 49 equals root of 65, which is approximately root of 65, it's approximately 8.1, which is not surprising considering it's just over 64. Okay. -3, 5, and 2, -2. Well, distance is root of x2 minus x1 squared plus y2 minus y1 squared. Which means root of x2, that's 2 minus -3 squared. Now the problem, if you have a convention of nesting without using nested round brackets if possible, is that if you find that you didn't actually need a square bracket, y2 is -2 minus y1, which was 5. Yeah, if you wanted to bracket these substitutions, you could, but it's not strictly necessary here. Squared. Okay. This is equal to the root of 2 plus 3 is 5 squared plus -2 minus 5, so -7 squared. So this is 25 plus 7 by 7 is 49. Which would end up giving us root of 74. which means 74 square rooted, it's approximately 8.6. So that is the distance between these 2 points. As we can see, Pythagorean theorem is good for quite a few uses. And, well, we reviewed radicals, like how square roots work. And what else? Well, we also reviewed the types of real numbers. So, integers, which are all whole numbers from negative infinity to positive infinity. Rational numbers, which are numbers that can be represented as a ratio between two integers. So a fraction between two integers. Irrational numbers, which cannot be represented that way. And natural numbers, which are positive integers plus 0. Or, depending on convention, just positive integers. Although why they would bother with that when you can just say positive integers, well, who knows. So yeah, natural numbers, because positive integers kind of exist as a group, usually they include 0, but I've seen them not. So just be careful of your conventions. There are also places where for some reason whole numbers just mean the natural numbers, which is really weird in my opinion, because, well, guess what, guys? -5 is a whole 5 units away from 0. Well, just so that you're aware, we discussed that this chapter, and that's it. See you next chapter.